Hello everyone. Today we will be continuing our discussion of scheduling problems with an overview of priority lists. Now, a priority list for a scheduling problem is basically just what order are we going to prioritize the different component tasks of whatever project we're dealing with. So the idea is that when we are following a priority list, we always want to be working on whichever tasks are available that are the highest up on our priority list. So let's make a simple priority list for this project diagram that we have up here. The simplest way to create a priority list for a project would be to just essentially list the tasks in alphabetical order and say that's our priority list. So if we do that, we have A2, B5, C3, D4, E4, F5, and then finally G2. Now, this is not a particularly, maybe not the most effective way to get a good schedule by just making a simple alphabetical priority list like this, but it is a priority list nonetheless. So what this basically means is that we want to start working on A as soon as we can, and then our next priority is B, then C, then so forth and so on. If we are working on the project and the next task on our priority list is not available yet, meaning the precedent tasks have not been completed yet, then we just skip it and we move to the next highest one that is ready for us to start on, basically. So when we are following a priority list at any given time, there's three different possible scenarios. One of them is that all of our processors are busy. So in the example that we'll be looking at in a second here, we have two processors, P1 and P2. So if P1 and P2 are both busy, then we wait until one of them is not busy, basically. The next scenario is one of our processors is available. And this basically, in this case, basically we are going to assign that processor whatever is the highest task on our priority list that has not been completed or currently worked or is not being currently worked on. In the event that there are no eligible tasks, then that processor just has to remain idle until there is an eligible task that can be worked on. The next scenario is we have multiple processors available, in which case we assign tasks to as many of those processors as we can in the order of our priority list. Now, it doesn't really matter which processor we assign which task because we are operating under the assumption that all the processors are going to take the same amount of time to finish any given task. So let's look at this example with our alphabetical priority list. So at the very beginning, we are going to look at whichever tasks have only the start as the precedent. So in this case, that would be A, B, and C. All three of these, we don't have to have anything done before we start on those because, again, the only thing that comes before them is the start. So when a task is ready, we are going to circle it to indicate that that task is ready to be worked on. So we're going to start, we have both of our processors, P1 and P2, available. So we are going to assign these two processors the first two tasks that are available on our priority list, in this case A and B. So A is going to take 2 hours to complete. Let's just say we're dealing with times and hours here. So what we're going to do is on our schedule down here, we're going to add a little bar for A that goes up to 2. So length of 2 because it takes 2 hours to complete. And then for B, we're going to have the same thing except it's going to be length 5. So we have B5. Note that once again, because we're assuming all tasks or all processors take the same amount of time to complete any given task, we could have easily switched which one we give to P1 versus P2, and it would have been exactly, it wouldn't have mattered, basically. Now, let's look at what is the next thing that happens. So the next thing that happens after we start is A becomes completed. Now, when tasks are being worked on, we're going to indicate that with a single slash through them. So we've started A and B, and then the next thing that happens is we finish A. So we're going to indicate that with a second slash through it, so we've got a little X over that to indicate that it's completed. So once A is completed, we're going to look up at our project diagram and notice that once A is completed, that opens up E. So E is now ready, but the next thing on our priority list is task C. So we're going to give P1 task C. And that's going to be 3 hours. So now you'll notice that we next have two things happening at the same time. B and C are both going to finish. So if we finish B and C, that's, if we look at our project diagram, we notice that that opens up task D. So task D is now available. So we are going to, we're basically going to assign P1 and P2 tasks based on the next available things in our priority list, which in this case are D and E. So as it works out, D and E are both 4 hours. So we've started on both of those, and actually the next thing that happens is once again both of those finish at the same time. So once those two finish, F and G are now both opened up. So we're going to circle those, and since we have two open processors, we can assign both of those tasks. So we're going to have F for 5, and G is going to be 2. So notice that this means that P2 is going to be idle for the last 3 hours while F is being worked on by P1. So this gives us a finishing time of 14 for this. So this is an example of how we make schedules using a priority list. In this case, we just used a simple alphabetical priority list. In the next couple videos, we'll talk about some other algorithms that we can use to help us develop priority lists. Ideally, we want to be as close as possible to the optimal priority list, which is basically just whatever priority list is going to give us an optimal schedule or lowest possible finishing time. Thank you for watching, and as always, I'm happy to help with questions.